Hello. Um, Hi, guys. So I'll be starting with reverse engineering, first day. So my name is Lakshmi, and I think we'll start. Okay. So basically, what is reverse engineering? Like, what what comes to your mind when you hear reverse engineering? Reverse engineering is basically like you're reversing something. What is reversing? Like, for example, you get this. You have a very it's just like taking apart this complicated wristwatch. At first, you see it as a fully functioning object, but then you want to understand how it works, so you fully disassemble it, examining each gear, spring, screw, etc. You map out the relations between the parts, you understand how each one contributes to another, to the timekeeping function. Eventually, you figure out the design and then how it fits together, and then by reassembling, you could even build the wrist from scratch. So, just like that, we are talking about reverse engineering like a software, like software or a program that has been given to you. So it is basically you're analyzing a system or a device or a piece of software, and you're understanding like the you have the binary code with you, but then you do not have access to the source code or the design documents or anything, and then you have to figure out, and then you're figuring out the structure, the components, the functionality, etc. So we have what is reverse engineering, or where do we use reverse engineering in the real world, and why should you do reverse engineering? Okay, now thinking about it, what is reverse engineering? I've already told you what reverse engineering is. Okay, so now I'll talk about where do we use RE in the real world. We use RE for like malware analysis. Take an example. Malware analysis. Malware is basically like a bad program. Like a bad program is like a bad program into your computer. Okay. So we can take the malware, and then you can reverse engineer the malware, and then you can understand how it operates, what damages it's causing to your PC, and then how it spreads. So by understanding what is happening in the malware, you can create, like you can make defenses against it, and then you can even patch like it. For example, this malware, it exploits certain vulnerabilities in your this thing. So you can see what vulnerabilities these are, and then you can patch those. So that's what I said. Like I said, vulnerability discovery. So like I said, you can by reverse engineering, you can also patch vulnerabilities in your PC, like any vulnerability, like any vulnerable point where attackers can come and attack. That's called an vulnerability. So you can patch it out. Patch it out as in like like make it not a vulnerability anymore. You can patch it out. So yeah, that's how it is. And then also, like for example, when take an example, and then your system gets compromised. Like for example, viruses. Your system has been compromised, and then now you have to understand, like you have to understand what's happening to your system. So there you can use RE. Like you can use RE to analyze what's going on, like what has happened, and then you can reconstruct the timeline. That's what happens. They reconstruct the timeline of events, and then they gather evidence, etc. So then another thing is, so that's it. There are more examples also, which I'll talk about later. So the next, going to the next part. There's why. There's the question of why. Why should you do RE? So RE challenges. Doing RE challenges basically enhances like, your analytical and problem solving skills, because it requires you to understand and break down the complex code and code obfuscations. You have to understand it and you have to break it down. Yeah, that's what you have to do. Also, yeah, that's why. Yeah, let's move on to the next slide. So, like I said, what is RE? Again, it's like a recap. Understanding it is. You can also call reverse engineering as basically the art of understanding. So, at its core, reverse engineering is all about gaining a complete understanding of a system, like a program or device. Often, you don't have access to the original source code. Like you just have the system, but you don't know how it's gotten here. Okay, then once you understand it, you can see how it's structured, how it operates, and what each part of it does. Then comes breaking or cracking or bypassing. So with a full understanding of the system, now you can discover like vulnerabilities, weaknesses, or any hidden thing. So this knowledge can then be used to bypass any. With this knowledge, like you know what's a weak point in this system. So you can if you want, you can exploit it, or if you want, you can patch it out. Yeah, you can do things like that. Then there is this enhancing. Third point is enhancing. So after understanding and breaking down a system, you can, like I said, patching is just enhancing. This might mean like there is an existing tool, like, yeah, you can enhance enhance like that. All right. So now, where do we use RE? Like these are just real life examples of where we use RE, reverse engineering skills. For example, game hacking. For example, some of you might play games. Most of us play games. So you have seen like there's game hacking. Like you can like you know RE can be used to, like, you can alter or you can bypass like the game mechanics, and then you can like you can gain this added advantage. So you can do that. This basically involves you to reverse engineer the game code, and then you have to understand which all game functions do what, and then you can modify it. That's called game hacking. License cracking, so, you have certain softwares require you to own a license, but then you can also use it without. You can, like I said, software license cracking. There are certain softwares that require you to own a license in order to play the games. But you can just reverse engineer the software. You can analyze its protection mechanisms, which may include like number checks or anything. And then by understanding how these checks work, you can create cracks or patches that disable these protections. And exploiting softwares, like I said before, once you thoroughly understand the structure of a software, if you find a weak point or if you find like a vulnerability, you can maybe like uh, add something over there to make it do what you want to do. That is, you can exploit it. That you can exploit the software, or you can make it do anything. You can add malicious code. You can do that. So just like everything, there's like a red side, and then there's like a blue side. So the red side is all about the game hacking and then the license cracking, etc. That is like that's one side of, like, everything has its two sides. This is one side of it, and then you have the respective blue side, which is basically, like, as you can see, anti cheat development and then antivirus development. Like, there is, in order to, just like there is cheat, you have also anti-cheat, so that people play games as it is. Okay, there is also this is also the case. Now, how to start RE, and how to start reverse engineering. First of all, you have to develop pattern recognition. Now that happens when you keep working on when you reverse engineer many codes. You happen to see the same code functions or code structures. You happen to come across them over and over again, so you gain this ability to recognize patterns. So this is a skill. I mean, it develops over time. Then you should also have like a strong understanding of computer internals. That is by studying computer architecture, CPU registers, memory management, etc., or OS, etc. Then programming skills. You have to strengthen programming skills in C or C++ and assembly, so that you can control memory at processes at low level. So yeah. So you have tools used in RE. You can see Binary Ninja, you can see Ghidra, you can see Angler. So I'll tell you there are three types of tools. There is this decompiler, there is a debugger, and there's a disassembler. Might sound like words. Might not have heard them before. So decompiler is basically that is the machine code. Decompile, what the decompiler does is, for example, you have a machine code. For example, you have a file. There you've given a file, and then you can use a decompiler to turn the machine code back into something closer to the source code or what it originally was. Tools like Ghidra, and there is another IDA. IDA is also another decompiler. You can use tools like Ghidra or IDA in order to do this. So you, by doing this, you can understand complex programs without having to dive into the assembly code. Like you get the source code. Then you have debugger. You don't. I None of these pictures are a debugger, and debugger is it lets you run a program step by step, checking what happens at each stage, and you can even pause. You can even look at the variables, and you can see how it changes as it runs. For example, the main example of debugger is a GDB. Then you have a disassembler. Disassembler basically takes machine code and it translates to assembly language, showing you what the computer is doing at a very low level. Tools like IDA Pro, Radar, and Ghidra let you view this assembly. So it helps you figure out how a program works under the hood. Next, talking about RE events. One that like to mention the main is Flare On. Flare On is one of the most popular reverse engineering CTFs, and you can also like these are the medals that they've given out throughout the years. Now I'm going to be talking about computer architecture. This is CPU. So computer architecture basically refers to the design of like how a computer's components and how they work together to execute instructions. Instructions are basically like when you have a program. In order to run that, it has like, certain instructions have to be made, and then your CPU executes these instructions. So at the core of this, you have the central processing unit, that is the CPU. So CPU performs computations and manages data. The key components of a computer include the CPU, memory, input-output devices, storage devices. So the CPU is often called the brain of the computer. You might know that. It executes instructions. Like I said, it processes data. Also, it consists of several main parts. That is the ALU and the CU. ALU is the arithmetic logic unit, which handles arithmetic and logical operations. Then you have control unit, which directs the CPU by interpreting and executing instruction. That is basically like it gives a control flow in what instructions to interpret and execute. And then you have registers, that is small fast storage locations within the CPU that hold the data and the intermediate results during computations. Okay. Memory plays a crucial role in computer architecture, storing both data and instructions. The CPU retrieves the instructions from memory for execution and interacts with the stored data. Memory is generally organized into primary memory, which holds the actively used data, then cache memory, then secondary memory. Like cache is faster, but it's smaller. Then you have secondary memory that like hard drives or SSDs for long-term storage. Memory hierarchy places registers, like I said, fast, small, and fast at the top, followed by cache, then RAM, then the storage devices. So the CPU executes instruction. I told you about it has to execute the instructions. It does this by using the fetch, decode, execute cycle. Basically, it fetches the instructions from the memory, decodes it to determine the action, then executes the operation. So communication between the CPU, memory, and other components occurs through the system bus. Just like the word means, like a bus, it basically takes data or addresses from one location and then it transports to another location. Then you have yeah, the OS basically mediates between software, hardware, like it manages resources, memory, input-output devices, etc. That is what the operating system does. Mediates between software and hardware. So basically, what happens is that an x64, it's like a CPU loads a program from storage to memory, then fetches, executes instructions, And then it uses like other things like stack, for example, to manage function calls. So the program ends when all the instructions are executed and the operating system frees the memory used. Now talking about assembly language. Assembly language often it is low-level programming language that provides a direct interface to the CPU's instruction set. It is just a level of abstraction just above the machine code. Like assembly language is like for example, we cannot read machine code, right? So assembly language is just you can actually say it as it's just like the binaries, like the zeros and ones for us to it is basically for makes it easier for us to read the machine code when it is in assembly, and it is just below the high level languages like Python or Java. So it is also very closer to the hardware. So yeah, yes, this is this is the code for a hello world, to print hello world in assembly. Okay, now we'll talk about compilation process. Compilation process as in you have a C source code, and you have to get C source code as in you write a C code, and then you want to run it. So when you run it, you run and then you get the output. It might seem like a seamless process, but it's not. There are in many intermediate steps in that is going on in this process. And first one is pre-processing. Pre-processing, it is not shown here. Pre-processing, what it does is it removes when you write a code, you can have comments, etc. Pre-processing, and then you have the header file, and then you cannot include like all the when you write a code, you cannot include all the code in that. You cannot basically, like I said, let me recollect myself. It removes the codes, it removes the comments, and then you see when you write a C code, you write include stdio.h. That is, you're including header files. This preprocessor stage, all these header files, all the files that you have included are all expanded. So after the preprocessor stage, if you look at the intermediate code, that will be that'll have the extension .i. You can see that it's huge. Like there's no include stdio.h. Then there are no comments. You can see that it's a huge code. After this, next comes the compilation. This is where things get serious. In that stage, the compiler takes that pre-processed code and translates into what we call the assembly language. Assembly language is a more readable, low-level language that represents the instructions that the machine will eventually execute, like I said for a while back. And during this step, it also checks for any syntax errors, etc. And it breaks down complex instructions into simple steps. After this stage, we're left with an assembly file. Now, after compilation, you have this assembly source code. Then here, an assembler takes that assembly code and converts into machine code. Machine code is a series of ones and zeros that the computer's hardware can directly execute. This machine code is then stored in an object file. At this point, still, we do not, however, still we don't have a complete program. Why? Because our code might rely on other code libraries. Libraries, like what are libraries? Libraries, like when you're writing a code, like when you're writing a program, you may write functions. Functions to you may have different functions. So you might have to use all these like many codes. You might have to use the same functions. But then that is a lot of that is not required. You can have all these functions in a standard library. Like you can get the code from that library. This is possible. So that could be a standard library, for example, and that is located that is there in your system. So then what happens is then comes the linking stage. In this process, you have your linker. Linker takes your object file and it combines with other object files, and it includes any libraries. That's what the linker does. And then finally, you get your executable file. Now this file is your finished program which is ready to run. So, like I said, there are zeros and ones, right? So the bit is the smallest, and that can be a zero or a one. Now you have a byte, which is 8 bits. Okay, then you have word, which is 2 bytes. Then you have a D word, which is 4 bytes. That is 2 words. Then you have a quad word, which is 4 words. That is 8 bytes. Now, this is the question. Now you can type it in the chat the answer for this question. You can I'll tell to you. I'll reveal it at the end. What 16 bytes together might be called. You can say it in the chat. All right. Now we talk about, as you can see, memory layout. Now you have a program. Now you're running the program. So running the program, then you're running a process. Like it comes a process, and you're running this process, and this is the memory layout of a process that is in memory. So here you can see many different sections. You can see text, you can see data, you can see uninitialized data, heap stack, etc. Text section, as you can see, text section, this is where the actual code of the program is stored. This is like the instructions that the computer follows to do its job. Like you might have seen here, like you have the text section and you have the data section also here where you store anything that you want to print, like variables. Then you have the data section. Data section is where you keep things like variables, global variables that is stored in data section. Then you have the BSS section. This basically stores the uninitialized data, like variables that the program hasn't given a value to yet. Local variables are, as you can see, stored on the stack. Then you have a heap, which is like an extra storage space. When extra storage space that the program can get more room when it runs out of space in the other sections. Then you have the stack. Okay. So now we'll talk about x64 architecture, which is the 64-bit version of the x86. It is commonly used in modern processors. This x64 enables larger handling, like it enables us to handle larger data sizes because it has 64 bits and faster computations also. Now, understanding the x86 register set is important for us. Is important for assembly language and reverse engineering and low-level programming all. So x86 has basically a broader register set compared to 32-bit systems. It allows it to handle more memory and process data. Now there are 16 general purpose registers and then special purpose registers, all 64 bits wide. This can be used for tasks like arithmetic, memory addressing, and, controlling a program flow, etc. Here you can see RAX, which is the accumulator. It is often used for return values. You have the base pointer for memory addressing. You have the RCX counter. And you have RDX, that is the data register. You have RSI, RDI, source index and destination index. Then you have the base pointer and stack pointer, RBP and RSP. Then you have R8 to R15 is the additional general purpose registers. But you also have special purpose registers apart from this. That is that is the RIP. That is the instruction pointer, program pointer pointing to the next instruction. You have R flags. R flags, it's like the CPU's scoreboard, keeping track of like results, like if an answer was zero or if something went over the limit, etc. So the CPU uses this info to decide what to do next in a program. So here and then accessing like you can, as you can see here, you can access parts of the registers. So in 64 you can access smaller parts of the 64-bit registers, like you can use the 32-bit, like this is the 32-bit, like EAX, EBX, etc. For the lower 32 bits you can use, you can just change the R to E. Then 16-bit AX or BX for the lower 16 bits, and then 8-bit for the that is AL or BL for the lowest 8 bits. All right, now this is basically the structure of an instruction, structure of an assembly instruction. Here you can see move A comma B. Here the move is basically opcode. It's called the opcode, and it tells you what kind of operation you want to do. That can be move. You can add, you can increment, you can decrement, you can multiply, you can divide. The operand is who we want to do the operation to, or anything. Now here the operands, as you can see, A and B. It can be from it can be registers, like it can be both registers. It can be, for example, move EAX comma EDX, or it can be move EAX comma an immediate value, that is like a number. And you can also use memory addresses. For example, move EAX comma a memory address. You can use those in the operands. Now we look at a few instructions, assembly instructions. Here you can see move RAX comma 1, move RBX comma 2. Here move RX comma 1 is that they're moving 1 to RX. Then move RBX comma 2, that is they're moving 2 to RBX. Here and then they're adding RAX and RBX. Here add is the opcode and then RX and RBX are the operands. Then subtract RX comma 2, that is they are subtracting whatever value is stored in the register RAX, they're subtracting 2 from it. Then they're incrementing RAX by 2, just like subtracting, they're incrementing RAX by 2. Comparing EAX to 5, that is like it compares the value stored in EAX with 5. And then as you can see, the last one, jump label, that is it jumps to whichever location the label is at. So we've reached the end of our session. I hope you've understood what I've said. And if you do have any doubts, you can post it in the Discord chat or you can post it in Telegram. Yeah. So in the next session, you'll be solving a crack me, and then you'll also be looking at the C code in depth. So that's all is there to the session. Thank you.